Hello everyone, welcome to topic 8.6, molecular structure of acids and bases. By the end of this, you should be able to explain the relationship between the strength of an acid or a base and the structure of the molecule or ion. The strength of an acid or base refers to the degree to which the Bronsted-Lowry acid, proton donor, or a Bronsted-Lowry base, the acceptor, dissociates in a solution. Strong acids and bases are generally considered to dissociate completely. The strong bases are all considered to be group 1 and 2 hydroxide salts, such as sodium hydroxide and barium hydroxide. Please note that beryllium hydroxide and magnesium hydroxide are excluded from this list. The stronger an acid is, the weaker its conjugate base will be, and vice versa. So a very strong acid will have a very weak conjugate base. So as shown here, it favors the forward direction. Okay, that's why there is no equilibrium arrow. When it is a very strong acid or base, it completely dissociates. Generally, this phenomenon is associated with a Ka value for acids and Kb value for bases of an acid that is greater than 1. Ka or Kb much bigger than 1. However, the 6 strong acids actually have variable Ka values. So as we see here, the strong acids have very, very weak conjugate bases. When compared with water, the basic contribution is negligible. Chloric acid, HClO3, is often referred to as a strong acid since its Ka value is also bigger than 1. And there's a link to the acid strength charts there. A weak acid or a weak base, however, does not dissociate completely in solution. Weak acids may be inorganic acids such as hydrofluoric acid or hypochlorous acid, or as organic acids such as acetic acid, where the acidic proton is here, which exists in equilibrium with the position favoring the reactants. Bases such as ammonia are considered to be weak bases, and two example general expressions for the chemical equation are shown here for both of them. So binary acids. The chemical structure of acids controls their relative strength. Bond length, bond strength, and electronegativities of atoms in the compound all play a role to the degree to which the Bronsted-Lowry acid will dissociate in solution. The following chart shows 4 acid halides, so that means halogens that have a hydrogen ion on them, so they're acids, and their pKa values. The lower the pKa, the stronger the acid. The chart shows in trend that the acid strength increases for binary acids down the group of the periodic table, with hydroiodic acid being the strongest and hydrofluoric acid the weakest. In this case, bond length and strength appears to play a major role. The hydroiodic or Hi bond in hydroiodic acid is the weakest of the halide acids shown above. This trend suggests that the longer and weaker hydrogen to halide bond, where X actually can be any atom, results in a relatively stronger acid than an acid with a shorter, stronger bond. And we can think about it this way. If it has a short, strong bond, it takes a lot more energy to overcome that intramolecular attractive force that keeps that bond there. However, if that bond is weaker, like for Hi, that bond is fairly weak because it is such a large molecule and that electron density is spread out. It is easier to overcome that attractive force. Also, because the electron density is more spread out over a larger atom, the iodide ion is much more stable on its own than the fluoride ion because the electron density is more spread out. So it's kind of like a weaker magnet and not going to attract as strongly. So that conjugate base, right, this is the conjugate base, is much weaker than this conjugate base. This conjugate base is fairly strong compared to the iodide ion, so it'll pull hydrogen ions in on occasion, making it a weak acid. Oxyacids. An oxyacid is a ternary made from 3 elements acid with one or more oxygens in its structure. Generally, an increasing number of oxygen atoms in an acid means that it is a stronger acid, thus a higher Ka and a lower pKa, due to the increased stability of the conjugate base because of an increase in resonance. So additional oxygens in an acid structure tend to increase the acid's strength due to the additional electronegativity. This is referred to as negative inductive effect. As electron density is drawn away, so oxygen, remember, is highly electronegative. It wants to pull the electron density towards itself. Well, with this, we have lots of electrons here, but this oxygen is going to attract some of the electron density towards itself. And because it's also then spread over 2 oxygen atoms, right, it's going to reduce the electron density that we would see traditionally as in the hypochlorous or hypochlorous acid or hypochlorite, ClO. Okay. As electron density is drawn away from the acidic OH bond in the structure, which is actually the one that's negative here, the acid equilibrium shifts to the right, so a larger Ka. So as we add more oxygens, this acidic oxygen, which is usually the one bonded to the hydrogen ion, is stabilized. And so that makes perchloric acid the strongest out of all of them. Other highly negative atoms also contribute to negative inductive effects on acids. We can also consider the stability of the conjugate bases, as I mentioned previously in the figure shown here. The perchlorate ion has 4 possible resonance structures, so it redistributes that negative charge amongst all of them, because they did experiments and they saw that it's not just rotating who has the single bond, but that they all have partial single and partial double bond character. And this stabilizes it and makes it the most stable out of all these 3 anions. So it is least likely to accept a proton because it's more stable, happy as it is, though like can a molecule actually be happy or an anion? But it's not reactive if it is stable, so it's going to hang out as it is compared to the perchlorous acid. There are some other inductive effects. Generally, a ternary or greater acid increases in strength when more electronegative atoms are included on the structure. For example, perchlorous acid is more acidic than hypochlorous acid is more acidic than hypobromous acid and then hypoiodous acid according to the chart. Because chlorine is more electronegative than either bromine or iodine, the OH bond is more likely to give up that proton due to the strength of the inductive effect. So chlorine is more electronegative. It's going to pull some of the electron density away from oxygen, weakening the H2O bond and making it a stronger acid because it's better able to give up that hydrogen. Highly electronegative atoms in a base's structure tend to make the base weaker for the same reason that they make the acid stronger. Electron withdrawal from the electron accepting the component of the base's molecular structure. Carboxylic acids are another structure that can donate hydrogens. The carboxylic acid functional group, which is this part right here, and we sometimes see it written as like this with stuff on this side, which we call that stuff R. The double bonded oxygen shows the same inductive effect by distributing that double bond and reducing the electron density that is on the acidic oxygen. So it's stabilizing it by resonance. Then we have nitrogenous bases. These are substances that contain nitrogen and have properties of bases. Some examples include ammonia and CH3NH2. You may be also familiar with the nitrogenous bases in DNA, adenine, guanine, thymine, and cytosine, or in RNA, and they're given here. Okay. So let's look at the IDU. Okay. How do you count for the difference in pKa of acetic acid, which is over here? So this is 4.76, and fluoroacetic acid, and its pKa is 2.59. So that tells me those two pKa values that the fluoroacetic acid is much stronger. Okay, well, we have to think about why. Well, the big difference is that fluorine is present, so fluorine must do something. So fluorine stabilizes the conjugate base through the negative inductive effect, or if we want to explain it, by pulling the electron density away away from the OH group, making the fluoroacetic acid stronger. Okay, so this is more electronegative. It's going to pull some of the electron density that is left when this hydrogen leaves, right? There isn't a fluorine over here, so it's just distributed amongst these two. However, some of the electrons go this way, which weakens this bond and also stabilizes the resulting negative charge when the hydrogen leaves. Okay. Nitrous acid, HNO2, is a weak acid with the given Ka and pKa values, while nitric acid is a strong acid with the given Ka and pKa values. Explain why nitric acid dissociates more completely than nitrous acid. Support your answer using Lewis structures. Now, that is important, so that tells us that how they're arranged on their structures is key. So for this one, that tells us that resonance is going to play an important part because these are very similar, right? But the addition of an oxygen makes a difference. So if we draw for nitrous acid, right? And I'm actually going to draw just the nitrous or nitrite compound. So we have this one. So after it gives up the proton, and because it's got this double bond, I know that I have resonance. So I know that that double bond can switch to this side and form this. So that means that the double bond is technically spread amongst this whole thing. So it's over a little bit of space. Now if we look at nitric acid, or the nitrate ion, my apologies, nitrate, NO3-, we have this. Okay, so this is one of the resonance structures for nitrate. However, that double bond can be distributed amongst all of them, or be on any of them. We could draw it anywhere. So let's do that. And this is resonance, so we're doing our Lewis structure that we were asked to do. So supporting evidence with Lewis structures. And then I have another one to draw, right? Because there's 3 oxygens that could have that double bond. And I forgot the negative charge. Right, so this one, if we were to draw its resonance, we would have the electrons distributed amongst all of those. So the additional oxygen on nitric acid provides more resonance which stabilizes the conjugate base more. Okay. So that concludes 8.6 notes. Please work on the you do, check your work, and thank you for tuning in.